Good day to all reasonable people. Today on Chronic HQ, we're doing a little technicum. We'll gawk at interesting pictures and talk about the most ridiculous, truly ridiculous military tech ideas of the 20th century. Not failed prototypes in general, there were countless, but the ones whose pointlessness was obvious before the first pencil line hit the drawing board. Some of them still made it into metal. Of course they did. To be fair, lots of sensible projects never made it or arrived too early/too late. We've discussed plenty of Third Reich rocketry, SAMs, anti-ship missiles that were conceptually sound but lacked the electronics, materials, and production base. Conversely, some things arrived too late. The V-1 cruise missile, for instance, could have been fielded 2 years earlier. All the industrial pieces existed. 2 years earlier, before Allied centimetric radar, proximity fuses, and jet/fast piston interceptors, London would have been scrubbed flatter than a parade ground. Timing is a thing. Brilliant ideas also get pushed out by other brilliant ideas. The Mirage 3, the icon of the 1960s, actually began life with a tiny liquid rocket booster inside, just for a few minutes of dogfight overdrive. Lovely on paper, miserable in service. By the time engineers finished wrestling with plumbing and maintenance, afterburners matured and made the whole concept redundant. That happens. A lot. But none of that is our topic. Today we're touring weapons so brain-dead that the stupidity was visible from orbit. And yet, into metal they went. Let's start with the Maus. Maus, the German super-heavy tank. Please admire the scale. Doorways look like dollhouse trim. The tank itself crawls. Height and width both about 3.7 meters. Think a one-story house with a pitched roof, rolling toward you. You can't hear the sound or smell the fumes, but imagine 180 tons grinding the earth, shoved forward by a 1,000 horsepower aircraft gasoline engine belching toxic clouds. If I saw that in real life, I'd die of fright on the spot. For the brave among you, it carried a 128mm gun, basically a heavy long-range AA cannon stuffed into a turret. Yes, it would punch through the front armor of any tank of its time, at any reasonable range. All crushing. Exactly Hitler's sort of thing, big for the sake of big. Two were built. Heinz Guderian later wrote that when a commission reviewed the design, he objected. The beast had nothing but that huge gun. No practical MG layout. So any man braver than me could just jog up and slap on a magnetic mine while the Maus tried to swat him with its trunk. Sorry, turret. But even Guderian missed the main problem. Trials revealed a detail that really should have been checked before cutting metal. No bridge can carry it. Imagine the process: designers, draftsmen, hundreds of engineers, machine tools, turret rings that don't hop off under recoil, electric transmissions driving motors on each bogie through reduction gears. All that, and nobody asked the adjutant to open a road atlas and read the weight limits on European bridges? Road signs say 20, 40, sometimes 60 tons. 180? No. Rail flat car? Too wide. So the solution was to string a gigantic power cable, park a megawatt generator by the river or a second Maus, seal everything against water, and drive along the riverbed. Whether the riverbed would hold 180 tons, unclear. Every tanker must be ready to die for the Führer, I suppose. In mid-1944 the order came, withdraw them. Weeks before Germany fell, both prototypes were blown up. Not a single combat shot. Fragments later rebuilt into the museum piece at Kubinka. The Maus gets a top-tier medal for nonsense, only because the next contender never left the drawing board. Behold the Landkreuzer P.1000 Rat. The Land Cruiser. The story strangely begins in Leningrad, where German engineers, barred by Versailles from tanks and heavy guns, played with ideas on Soviet soil in the late 1920s. One became obsessed with a 1,000-ton land battleship. Too much even for Soviet tastes. But Hitler loved big. So the pencil sketches returned to Germany. This colossus would prowl city blocks and simply push down buildings. Height 11 meters, a 3-story house. Width 14, length 35. Main armament, a twin 280mm naval turret, the actual main battery from a Scharnhorst-class ship, plus a 128mm little gun for enemy tanks, 8 twin 20mm AA mounts, a crew of 22, a bathroom, and 2 BMW motorcycles inside for scouting and medevac. Of course, Albert Speer finally killed it in 1943. Good. Compared to that, Maus really was a mouse. Now the piece de resistance of military absurdity that actually fought. The 80.7 centimeters railway gun. Two were built by Krupp, Dora, named after the chief designer's wife, and Schwerer Gustav. No full photographs survive because you couldn't fit the thing in a lens. So we get fragments and reconstructions. Barrel length, 32.5 meters. Total mass, about 1,350 tons. Not a typo. This was no ordinary railgun. It ran on 4 parallel tracks, 2 pairs. The firing position had to be purpose-built in a giant mustache pattern, so the mount could creep a few meters left or right to change azimuth. Construction time for a position, roughly 6 weeks, after you'd cleared and leveled a huge site. Shells? 2 types. He, 4,800 kilograms at minus 820 meters per second, Mach 2.4. Concrete buster, 7,100 kilograms at minus 720 meters per second. Muzzle energy on the order of 1,700 megajoules. An iconic German 88mm AA gun has minus 3 mj. This is 600 times more. It burned minus 900 kilograms of propellant in minus 6 milliseconds at minus 2,500 atmospheres. The barrel alone weighed minus 400 tons. The cradle and bogies had to absorb recoil that would otherwise yeet the gun into the next county. Price? Sources vary between 7 and 10 million Reichsmarks for the 2 guns and limited ammo, call it obscene. And what for? In World War I, Big Bertha, 42 centimeters, made sense. Aviation was infant, and there was no other way to lob a 1-ton projectile 10 to 14 kilometers. In World War II, however, a 5-ton shell isn't impressive if the explosive inside is only minus 700 kilograms, or minus 250 kilograms, AP. Why so little? Because the shell must survive minus 2,700 G at the start of travel. Otherwise it collapses in the bore and explodes the barrel. Thick walls, little filler. Meanwhile, a standard 1,000 kilograms Luftwaffe bomb carried minus 530 to 620 kilograms of explosive. The 1,800 kilograms class carried close to a ton. An aircraft can actually go places. For the price of one giant gun, you could buy a couple squadrons of Stukas or Heinkels, each flying many missions, with no need to build a 2-month rail labyrinth every time you want to pivot 30 degrees. Did it at least work? Dora was dismantled into dozens of loads and shipped to Crimea. Setup began after the February 1942 decision. First shot, June 5th. In 21 days it fired 47 combat rounds, then 5 test shots into the Black Sea. The other gun never fired in anger. Chief of the Army General Staff Franz Halder wrote the perfect epitaph. A true work of art, absolutely useless. Yes, aircraft beat railway guns. But let's remove that airfield caveat and compare gun versus rocket for the same mass of solid propellant. A gun spends its propellant instantly inside a short barrel. To reach range, it must dump all energy into the projectile at ground-level density, creating monstrous accelerations and drag losses right where air is thickest. The projectile exits at maximum speed and then only loses energy. Even for a high-quality system with minus 820 meters per second muzzle velocity, by impact the speed is subsonic. The projectile delivers perhaps minus 12.5% of the kinetic energy it left with. Inside the barrel, only minus 25 to 30% of the powder's energy becomes projectile kinetic energy at all. Minus 40% blasts out as hot gas, minus 20% dies as friction and heating. Multiply through and your locomotive efficiency is minus 4%. Charming. A rocket does the opposite. It accelerates gradually, accepts modest structural loads, 10 to 12 G rather than thousands, so its case can be light. It creeps through dense air slowly and saves the big acceleration for high altitude, where density is 14 times lower at minus 20 kilometers. No recoil structure, no 1,000-ton mount. The exhaust is your reaction mass. Result: vastly better use of the same chemical energy for moving a payload from A to B. If rockets are so smart, where were they in 1500, 1600, 1700, 1800? 2 big reasons, plus 1 practical. 1. No thin, strong, cheap tubes. Medievals could cast for 5-ton bronze cannon and even forge monstrous iron barrels from bands and hoops. But making long, thin, seamless steel tubing? Not until the Mannesmann brothers, patented 1886, and later mass production of drawn/seamless and then welded tubing in the late 19th, early 20th century. Your humble rocket motor case is just that, a reliable thin tube. 2. No stable solid propellant grains. Gunpowder explodes, technically deflagrates very fast. Rocket motors need slow, predictable, uniform burning grains that store safely for years. That demands industrial chemistry, precise binders, casting/pressing processes, and grain geometry to shape thrust curves. That's 20th century science, not alchemy. 3. Use case logic. A 15th century army wanted to smash city gates, breach walls, or punch holes in wooden hulls. Big, slow stone throwers did that job, could be cast once and used for decades of looting. A small rocket with tiny energy? Nobody would have paid even 1 ox for it, let alone 1,100. So yes, people who could forge an 800mm hoop-built cannon somehow couldn't make a reliable little steel tube with a slow-burning grain. Not until bicycles, chemistry, and industry caught up. And that, after staring at the strangest guns of World War II, is the real lesson. Chemistry, materials, and logistics beat gigantism. We'll save the next chapter, Soviet projects that killed nobody directly but still cost lives indirectly, for another day. Thanks for watching. If you enjoy thoughtful takes on how technology and history intertwine, consider subscribing. It helps me bring you more stories like this one.